Welcome back, guys. In this video, we're describing areas with double integrals. We're going to talk about two ways to describe area with double integrals, and then we'll do some examples. We did this a little bit at the end of the last video, but just to recap, let's say you've got what looks like a traditional area between two curves from Calculus 1. So you've got y equals f of x up here and y equals g of x down here. X equals 1 over here, or excuse me, x equals a over here, and x equals b over here. And you want to find the area between two curves, but you don't want to represent it as the area between two curves integral from Calculus 1. You don't want to represent it as a single integral. Instead, you want to represent it as a double integral, because maybe this is the region that we're integrating over for some function of two variables, f of x, y. Maybe there's a surface sitting above this region, and we want to find the volume under the surface. In that case, the way we would describe this region is this way. We would draw rectangles this way. That helps me a little bit. Draw vertical rectangles so that the bottom of the rectangle always lies on the function g of x, and the top of the rectangle always lies on the function f of x. Here we see that y goes from a function to a function. So it goes from the bottom function, g of x, to the top function, f of x. Well, x goes from a constant to a constant. So x starts over here and ends over here. If that's the case, and I want to represent this area as a double integral, I would integrate with respect to y first, because y goes from a function of x to a function of x. You go from the lower function to the higher function, bottom function to top function, and x goes from a constant to a constant. We would do that last. And the reason we do this is because when we integrate this with respect to y, and then replace y with f of x and g of x, then we just end up with a regular integral, a regular Calculus 1 integral with respect to x. Just to prove that we get exactly the same thing that we've got using calculus when we learned about the area between two curves, let's antidifferentiate this with respect to y. The antiderivative of 1 with respect to y is, of course, y, and we're integrating from y equals g of x to y equals f of x. So we substitute in the upper limit and the lower limit by the fundamental theorem of calculus and subtract. And look at that, you got the same formula that you got back in Calculus 1 when you learned about the area between two curves. So this is just an alternate way for representing this. And again, the reason that we're doing that is because we're going to find volumes under surfaces later, and the way we describe that region R that we're integrating over is like this. We need to describe the regions with double integrals. So if y goes from a function to a function and x goes from a constant to a constant, we do this, integrate with respect to y first and then x. Constants always go on the outside, and these functions for y, they can depend on x, but they can't depend on y. They're representing curves. Y equals f of x and y equals g of y. I don't want y to equal f of y. I hope that makes sense. I just want a function of x over here and a function of x over here. And then when we integrate, when we replace y with f of x and g of x and subtract, we end up with a regular Calc 1 integral. Okay, so that's what we do if y goes from a function to a function and x goes from a constant to a constant. Now, it could also go the other way. We might have x going from a function to a function, and y may go from a constant to a constant. So maybe I'm trying to find an area that looks more like that. Well, in this case, I don't want to draw my rectangles vertically, because over here, like the top function is this curve for a while, and then for a bit in here, the top function is that curve, and the bottom function is also given by the same curve. It just gets complicated. But if I draw my rectangles horizontally, it's not complicated at all. X is going from this function to this function the whole time. The bottom of that rectangle, or the left side of that rectangle, is always on the function x equals g of y. And the top part of the rectangle, or you can think of it as the right side of the rectangle, is always on the function f of y. So here, x is going from a function to a function, left to right, function of y to a function of y, and y is going from a constant to a constant. Y goes from c to d. So in that case, we would represent area this way. Since x goes from a function to a function, we integrate with respect to x first. And we go from the bottom function to the top function. Or, looking at this picture, from the left function to the right function. Smaller y values to smaller x values, to larger x values. And y is going from a constant to a constant over here. Now, there are some cases when both of these work, and then you get to choose generally. And there are some cases when you can represent the area of the region this way, but because of the integrand, because we're integrating some function f of x, y over that region, it might make more sense to use a dx dy integral as opposed to a dy dx integral because of what would come out of the integration. But we'll get to that when we get to volume later. So that is the two ways that we describe area with double integrals. Either we integrate with respect to y first and then x, or x first and then y. But the way we're thinking of it is this. Y goes from a function to a function, and x goes from a constant to a constant, that's this. Or x goes from a function to a function, and y goes from a constant to a constant. So let's do some examples. Start with this first example. Let's say someone asks you to express the area of the region as a double integral, and then evaluate the integral. So then find the area of the region. I'm going to call my region R. Oops. Okay, so let's say R is the region bounded by these curves. Square root of x plus square root of y equals 2. Y equals 0. And x equals 0. Okay, like what on earth does that look like? It's not a familiar function, is it? Okay, let's see. If I'm taking that equation and I'm rearranging it so that I can get a better sense of what it looks like, the first thing I would normally do is just get y by itself. So we will subtract square root of x from both sides. And then to get rid of this square root, we'll square both sides. We get this. Y equals 2 minus the square root of x quantity squared. Oh dear, what does that look like? If I write that twice in FOIL, I get first times first is 4. Outer times outer is 2 times the square root of x. It's negative 2 times the square root of x. Inner times inner is just like it. So I get negative 4 root x. And then last times last is square root of x, or negative square root of x times negative square root of x, which is a positive x. So y is equal to this. And what else do we know? y has to be greater than or equal to 0, and x must be greater than or equal to 0 for both of these to be well defined. So we're definitely in quadrant 1 because that's satisfied. Now this is not a function I'm familiar with, so I'm just going to be guessing. My sketch is going to be pretty rough, but it's going to be enough to help us write the double integral. So we know we're in quadrant 1. What else do we know? When x equals 0, we can see that y is equal to 4. Or you could just substitute an x equals 0 here. When x is 0, we get square root of y equals 2, so y is 4. And when y equals 0, square root of x equals 2, so x equals 4. So it looks like that. Now, 4 minus a square root function, like that would normally look like this. But then we're adding x to it, so it just looks a little funny. I'm not 100% sure what happens in between, but I suspect, I know it's continuous, that it looks something like that. And we also know that we're bounded by y equals 0, which is the x-axis, and x equals 0, which is the y-axis. So our bounds are this curve, which we're really not 100% sure what it looks like. That's okay. Y equals 0 and x equals 0. So clearly this is our region. Now I want to express the area of this region as a double integral, and then I want to find the area of R. So I've got a couple of options. The way this looks, it looks like I can write this as an integral with respect to x first and then y, or with respect to y first and then x. Either way will be fine, because if I draw my rectangles vertically or horizontally, either way, the rectangle will have the same bottom function and the same top function the whole time. If I draw my rectangles vertically like this, the bottom function is y equals 0, the top function is y as a function of x along that curve, which is given by this equation. Or if I drew my rectangles the other way, the left function is the same the whole time and the right function is the same the whole time. Since that's the case, either way will work just fine. So let's do it both ways, and then we'll see which integral we want to evaluate. Okay, so this curve, let's see, is square root of x plus square root of y equals 2. And we did some algebra earlier. We solved this for y, and we said y was equal to 4 minus 4 times the square root of x plus x. That's equivalent to that, provided that y and x are both positive. Well, and clearly x is positive from this, but we're also forcing y to be positive as well. So using this version of this equation, I say y goes from a function of x to a function of x. The bottom function for y is just 0. Y is equal to 0 on the x-axis, and the top function is this. And I'll write it as an x to the 1/2 power because that'll make it easier to integrate in a little bit. So y goes from a function to a function, and x goes from a constant to a constant. X starts at 0 and goes to 4. So one way to represent the area of this region is to integrate with respect to y first, because y is going from a function to a function. And then we integrate with respect to x, and x goes from a constant to a constant. Now this may not be what it looks like, but I know that the curve is up here somewhere. I know this much. So yeah, this is good enough for us. It's good enough to correctly set up the double integral. All right, now that's not difficult to evaluate. Let's think about the other way that we could represent this area. Instead of letting y go from a function to a function, and letting x go from a constant to a constant. We could do it the other way around. We could do it like this. We could think of x as going from this left function to this right function, and y going from a constant to a constant. Let's do the easy part first. Y starts at 0 and ends at 4. That's coincidentally the same bounds for x on the first one, just a coincidence. And then over here, we're going from this function to this function. Well, that line is represented by x equals 0. And on this function, if I solve for x, I get square root of x equals 2 minus the square root of y. Square both sides. And I think we're going to get pretty much the same thing as we got right there. Just replace all the x's with y's and the y's with x. Because of the symmetry of that equation, it turns out to be pretty much the same thing. So x goes from 0 to 4 minus 4 times the square root of y plus y. So we could represent the area this way, or we could represent the area this way. The integral from 0 to 4 of the integral from 0 to 4 minus 4 times y to the 1/2 plus y dx dy. Either one is fine. Now, it is just because of the symmetry of this equation that these are pretty much exactly the same. We'll see one in a second that's not so similar for the dx dy integral and the dy dx integral. Now you can evaluate either one of these to find the area of the region. Since this one's down here, I'll just integrate this one. They're pretty much the same, so there's not really an integral that's simpler in this case. We integrate 1 with respect to x. You always work on the inside first and work your way out. The integral of 1 with respect to x is x, and we're evaluating from x equals 0 to x equals 4 minus 4 times y to the 1/2 plus y. So you're replacing the x's with these functions of y. When we replace x with this, we get 4 minus 4 y to the 1/2 plus y, and then we're subtracting 0 by the fundamental theorem, but subtracting 0 doesn't do anything. So we're here. Now we just have a regular calculus 1 integral. Anti-differentiate with respect to y. The antiderivative of a constant with respect to y is just the constant times y. Then we bring the 4 down. Over here we add 1 to the exponent. 1/2 plus 1 is 3/2, and then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by the reciprocal, multiplying by 2/3. I might write that 4 as a 4 over 1. And then over here, add 1 to the exponent and divide by the new exponent. Substitute in 0 and 4 and subtract. And so we've got 4y minus 8 over 3 times y to the 3/2 plus 1/2 y squared. Just simplifying, evaluated from 0 to 4. And we get 4 times 4 is 16 minus 8/3 of 4 to the 3/2 plus 1/2 of 4 squared, so half of 16. That's all evaluated at 4 minus 0. Now, 4 to the 3/2 is the square root of 4 cubed. Now, if you don't remember that, let me just write that rule down for you. Remember, if you have x to the m over n, that's the nth root of x to the m. Or, if you want, you can take the nth root of x first and raise it to the m. Now, most of the time when I'm rewriting algebraic expressions, I use this first one. We go from here to here and vice versa. But when I'm working with numbers, when I actually want to evaluate something like this 4 to the 3/2, I usually do this one, because taking the nth root makes the number smaller, and then I just raise that number to a power. So take the square root of 4, which is 2. 2 cubed is 8. And so we get 16 plus 8 is 24, and we're subtracting 8 over 1 times 8 over 3 is 64 over 3. And I'm just going to use my calculator for the arithmetic. I get 8/3. Saying, what was that again? Oh yeah. 8/3 is the area of that region. It's 2 2/3, 2.67. That's how many, that's the area of that. Now, it doesn't look like 2.67 from the way I've drawn it, but that might be because this curve is not exactly right. That curve is just something that I made up that I knew would satisfy the conditions necessary to draw this, or to write these two integrals, but it might not actually be an accurate representation of this curve. I'm not really sure what's going on with the slope, the concavity. I'm not really sure what happens in between. But apparently, the area of the region is 8/3. Okay, so that's one type of problem. Might be given some region and asked to express the area as a double integral or 2 double integrals, and then evaluate them to find area. Now, sometimes you're given an integral and you're asked to sketch the region and also evaluate the integral. So let's say we're looking at this one. We've got the integral from 0 to 1 of the integral from y squared to the cube root of y dx dy. And we're asked to sketch the region R. So this is the area of a region R. We're asked to sketch the region R and then find its area. We can easily find its area right now, but sketching it, let's do that first. Okay, now these innermost bounds go with the innermost variable, and they tell us x starts at y squared and ends at the cube root of y. So I'm going to write that down. X goes from y squared to the cube root of y. And then on the outside, we've got this. Y goes from 0 to 1. Okay, well, what does that look like? In order to sketch this, I'm always thinking of this as 4 different equations. That's a horizontal line and that's a horizontal line. We've got y equals 0 and y equals 1. And then I have y equals x squared. That's one type of curve. And then I've got x equals the cube root of y. That's another type of curve. And we put all those pieces together to sketch the region. Now, I still don't tend to think of x as functions of y very easily, so I might solve those for y. At least that x equals y cubed one. But let's write down the 4 curves. We've got x equals y squared. We know that's a parabola on its side, so it looks like this. Y goes from 0 to 1. Y equals 0 is here. Let's say y equals 1 is here. And if this is x equals y squared, when y is 1, x is 1. Okay. And what else do we know? So we have y equals 0, y equals 1. Those were easy to sketch. We got x equals y squared. These are all of the bounds of our region. Oops. And then the last part is x equals the cube root of y. Now, x equals the cube root of y is not what I'm comfortable thinking about. It's not something that comes naturally to me. I can think about y equals the cube root of x and then switching the roles of x and y. It's easier for me if I just cube both sides. So I think I'll do that. If I cube both sides, I get y equals x cubed. And I know exactly what y equals x cubed looks like. It looks like that. Of course, this is not to scale. So I want the region that's bounded by x equals y squared, y equals x cubed, y equals 1, and y equals 0. Oops. I think it might be time for new highlighters. That's that region right there, guys. Well, I think we can represent that lots of different ways. So that's our picture. That's the region R. We can find the area of R by just evaluating that integral there. And I think I'll write that cube root as a 1/3 power. Because remember, x to the m over n is at the nth root of x to the m. Whatever's in the denominator, that's the index of the root. So that index is 3 here, so that I've got a 3 in the denominator, and there's an implied 1 there on the y, so there's a 1 in the numerator. And we're integrating with respect to x first, and then y. The integral of 1 with respect to x is just x. And we're integrating from y squared to y to the 1/3. So I replace x with its upper limit, y to the 1/3. I substitute in the lower limit, and I subtract. Now notice, that's like having the rectangles this way. X goes from y squared to the cube root of y, which is that one. Okay. And then we integrate with respect to y, just a regular Calc 1 integral now. So we add 1 to the exponent and divide by the new exponent. Dividing by 4/3 is the same as multiplying by 3/4. Add 1 to the exponent here, divide by the new exponent. Substitute in 0 and 1 and subtract. And we get 3/4 minus 1/3. Just get a common denominator. Multiply this one by 3 over 3. Multiply this one by 4 over 4. That worries me. Do you see the problem? Oh no, I made a mistake. I made a mistake in my arithmetic in my head. I just had 3 minus 4 in my head. It's 9 minus 4, so that's 5 over 12. Good. I was like, I thought I had a negative area for a minute. Okay. So the area is 5/12. It's a little bit less than 1/2. That's the area of that region. Now, we could have described that region differently. This said, we're integrating with respect to x first and then y. So x goes from a function of y to a function of y, and y goes from a constant to a constant. We could also describe this region in the other way. We could integrate with respect to y first and then x, and we should still get the 5 over 12 when we're done. Let's think about it. So y goes from the bottom function to the top function, and x goes from a constant to a constant. So x is going from 0 to 1, and y is going from this function, which we've already solved for y. Y is equal to x cubed there. And then this function. Now, I already know that x is equal to y squared here, but I need x, or excuse me, I don't need x as a function of y anymore. These are bounds for y. I need y as a function of x on this curve. So we will solve for y, and we get y equals the square root of x. And that works. It's a positive square root because it's the part of that parabola where y is positive. So square root of x. Okay, so another way to represent the same region, instead of doing this integral, we could do this integral. x goes from 0 to 1, constant to constant on the outside, and y goes from x cubed to the square root of x, which is the same as x to the 1/2. Okay, now if we evaluate that, we should still get 5/12. Let's do it, just to make sure. The antiderivative of 1 with respect to y is just y. And then you replace y with its upper bound and its lower bound, and you subtract by the fundamental theorem of calculus. So we get an x to the 1/2 minus x cubed, and we're integrating with respect to x. Okay. Then here we add 1 to the exponent. 1/2 plus 1, it's 1/2 plus 2/2 is 3/2. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then over here, the power rule, add 1 to the exponent, divide by the new exponent, substitute in 0 and 1 and subtract, and we get 2/3 minus 1/4. Now if I get a common denominator, I get 8/12 minus 3/12. 8 minus 3 is 5. Hey, we get exactly the same area. So it does not matter if you write the area of the region this way or if you write the area of the region this way. They're both going to give you the same area. They both represent this. Now later when we do volume under surfaces, depending on the nature of the integrand, it might make more sense to integrate with respect to y first then x, as opposed to integrating with respect to x first and then y. We'll see some examples in a little bit. But that's how we represent area with double integrals. Now there are some problems that can only be written, or that are easiest written this way, integrating with respect to x first and then y, or easier written this way, integrating with respect to y first and then x. Again, let's bring those pictures back. If the region looks like this, it makes much more sense to integrate with respect to y first and then x, because these vertical rectangles all start at y equals g of x and end at y equals f of x. If I tried to draw my rectangles horizontally, well, x would go from A to B most of the time, except for up here. Then it would be weird. It would be very difficult to describe a little area of a rectangle here and area of a rectangle here. This is simple. This is simple, vertically simple. Over here, like this is very simple if I draw my rectangles this way. The bottom of the rectangle, or the left side of the rectangle, is always on this function, and the right side of the rectangle is always on this function. So there are some cases when this is the way to do it or this is the way to do it, but there are a lot of cases like this one and the last one we did where it doesn't really matter which way you go. The region can be described both ways, and then it's really up to you. And when you're using this, when this is the region that you're integrating over with a function of two variables sitting above it, one of those ways might make more sense depending on what the integrand is. Okay, so that's it for integrals. Integrals representing area. In the next video, we'll talk about integrals representing volume.